Hello, welcome to my video series of algorithms. This is part 7 of Module 1, Sorting Algorithms. In this video, we will discuss the merge sort algorithm. Merge sort is another sorting algorithm that has an O n log n time complexity. Merge sort does not depend on advanced data structures and can be implemented easily with recursion. However, it is less space efficient compared to heap sort. While it still has linear space complexity, it is not an in-place sorting algorithm. The name merge sort comes from the merge procedure in the algorithm. The merge procedure can merge two sorted lists into one sorted list. The merge procedure works as follows. Given two sorted lists, list 1 and list 2, we initialize two pointers p1 and p2 point to their first elements respectively. We will also allocate an empty array to store the sorted elements. Now, we begin by comparing the elements that are pointed by the pointers. When sorting in ascending order, we put the smaller element into the merged list. For example, here we have 4 and 1 being pointed by the pointers, and 1 is smaller than 4, so we put 1 into the merged list. After that, we also increase the pointer p2, as the element it was pointing to has been processed. We then repeat the process by comparing the elements pointed by the pointers. We found 2 is smaller than 4, so we append 2 to the merged list. And we increase the pointer that was pointing at 2. Similarly, we continue the process and append 4 to the merged list. And we increase the pointer that was pointing at 4. We then append 12. We increase the corresponding pointer. We compare 13 and 17 and append 13 to the merged list. And we increase the pointer p1. Note that at this stage, the pointer p1 has been moved to the end of the list 1. It means that no more elements in list 1 need to be appended to the merged list. In this case, we can directly append the remaining elements in list 2 to the merged list. So, we append 17 to the merged list, and we are done with the merge procedure. Here is the pseudocode for the merge procedure. L1 and L2 are the two input lists, and Lout corresponds to the merged list. P1 and P2 are the two pointers. The while loop iterates the following 3 steps: compare, output, and increase pointer. Finally, after one of the pointers hits the end and the while loop terminates, we append the remaining elements to the merged list. We claim that the merge procedure is correct. We can argue by showing that the element selected in each iteration is the smallest one within the remaining elements. Without loss of generality, say list 1 P1 is selected after comparing with list 2 P2. Because the two lists are sorted, all elements after list 1 P1 are larger than or equal to list 1 P1, and all elements after list 2 P2 are larger than or equal to list 2 P2. Meanwhile, because list 1 P1 has been compared with list 2 P2 and is selected, we know list 2 P2 is also larger than or equal to list 1 P1. Taken together, all elements that remain unexamined are larger than or equal to list 1 P1. So, list 1 P1 is the smallest one. Since the merge procedure always outputs the smallest element remaining in the set, it can produce a sorted list. The merge procedure runs in O(n) time, where n is the number of elements in the output list. This is because the procedure outputs one element after each comparison. Since there are at most n elements to output, the number of comparisons is also upper bounded by n. Now, we have the merge procedure that is capable of merging two sorted lists into one. We'll use it to develop a sorting algorithm. Recall that our goal is to sort all n input elements. Imagine if we split the n input elements into two subsets and sort each subset individually, we will obtain two sorted lists. Then we can apply the merge procedure on the two sorted lists and obtain a sorted list with all n input elements. Say we will split the n elements evenly. Then the problem becomes whether we can sort the two subsets that each contains n over 2 elements. Well, we can sort n over 2 elements if we further split them into two subsets of n over 4 elements and sort each subset. You can see that the recursion goes on and on until we have reached subsets of size 1. In this case, we don't need to sort the subset anymore because a single element is considered sorted. Here is a schematic diagram of the merge sort algorithm. The left-hand side of the figure shows how the sets are decomposed phase by phase, and eventually reach sizes of 1. The right-hand side of the figure shows how the smaller sorted subsets are merged into larger sorted subsets using the merge procedure. You can see that the shallower the layer, the fewer merge procedures are required, but each is applied to larger inputs. The deeper the layer, the more merge procedures are required, but each is applied to smaller inputs. This is the pseudocode for the merge sort algorithm. Note that it is a recursive algorithm, so it calls itself during the execution. Lines 2 to 5 specify the boundary condition that allows the termination of the recursion, where we have reached subsets of size 1. Line 6 partitions the input set into 2, and line 8 sorts each subset by recursively calling the function itself. Finally, in line 9, we call the merge procedure to generate the final sorted list. Now, let's analyze the merge sort algorithm. We can prove the correctness of the algorithm using mathematical induction. We will take the base case as that sets containing only one element are sorted. Then, due to the correctness of the merge procedure, all size 2 lists are sorted. Then, all size 4 lists are sorted, and so on. Eventually, we can reach a certain point where the size n list is also sorted. For the time complexity, first recall that the merge procedure takes O(n) time, where n is the number of elements in the output list. Recall this diagram. It is easy to see that each layer contains n elements. It means that to generate the sorted list in each layer, the total effort required by the merge procedure is O(n). Then, we see that there are O log n layers in total. This is because the algorithm halves the input set each time as it goes to a deeper layer, and it takes O log n halves to reduce the set size to 1 from n. Taken together, the time complexity of the merge sort algorithm is O(n) log n. Now, let's analyze the space complexity. We can see that a direct implementation of the algorithm based on the diagram would need O(n) log n space. This is because we have O log n layers and O(n) elements in each layer. However, note that after the merge procedure, its two input lists will not be accessed anymore and can be released or overwritten. It means that when running the merge procedure, the arrays holding the inputs can be used to hold the output of the next phase. That is, we only need to allocate two size n arrays, a pink one and an orange one. At the ith phase, we will use the pink array to hold the input and the orange array to hold the output. And at the i+1 phase, we will take the elements stored in the orange array and output the result to the pink array. All data can be moved between the two arrays. Therefore, the space complexity of the merge sort remains O(n). However, as it uses more space than what is necessary for holding the input, the merge sort algorithm is not an in-place sorting algorithm. In summary, we have discussed the merge sort algorithm in this video. The merge sort algorithm can be easily implemented using recursion. It has an O(n) log n time complexity and O(n) space complexity. However, It is not an in-place sorting algorithm. Thank you for watching and see you next time.